430 million years ago, Earth shimmered in renewal. The scars of past extinction had faded beneath shallow seas where coral gardens bloomed and armored fish drifted through light like living metal. Continents were stirring, climates steadying, and the first forests of moss and root clung to stone. Life, for the first time, found rhythm in both sea and land, a fragile balance between stability and change. But beneath this calm, the planet was not still. The Silurian world was learning how to breathe and how to dream again. When the seas stilled, in the silence that followed the catastrophe, Earth seemed to hold its breath. The late Ordovician mass extinction, one of the deadliest events in the planet's deep history, had erased nearly 85% of marine species. The oceans, once teeming with trilobites, corals, and planktonic clouds of life, had fallen into stillness. Ice sheets had crawled across Gondwana, lowering sea levels by more than 100 meters and exposing continental shelves that had never seen sunlight. What had been an oceanic paradise was reduced to silt and bone. The Silurian dawn began in this uneasy calm, a planet between breaths, waiting for life to return. Across the continents, silence ruled. Laurentia, Baltica, and Avalonia, three ancient landmasses that would one day unite to form the northern supercontinent, Laurussia, lay bare beneath a thin, ochre sky. Only microbial films clung to the rock, darkening their surfaces like the faint memory of life. The atmosphere was thick with carbon dioxide, possibly 20 times higher than modern levels. And yet the air was starved of oxygen, hovering near 14%. These conditions defined the opening of the Silurian period around 443 million years ago, when the planet struggled to recover its equilibrium after the climate swung violently between ice and heat. In the oceans, where most life still lingered, the aftermath of extinction played out slowly. When those glaciers began to melt at the start of the Silurian, they released torrents of mineral-rich runoff into the seas. This sudden infusion altered ocean chemistry, increasing calcium and carbonate availability, fueling the reformation of reefs and shells that would one day define Silurian biodiversity. Isotopic evidence from limestone layers in Scotland and China tells this story in fine detail. Sharp shifts in carbon-1, 3 levels marking collapse, recovery, and renewal. Beneath the waves, survivors drifted through a transformed seascape. Graptolites, colonial planktonic organisms that once spanned the globe, hung on at the margins of extinction, their diversity reduced to a fraction of its former scope. Trilobites, resilient yet diminished, retreated to deeper waters. Brachiopods, those ancient shell-bearing animals, began to reclaim their niches, clinging to hard substrates in shallow seas that were gradually warming. The Silurian world was not yet rich in life, but it was stable, and in that stability lay the conditions for evolution's return. Sediment records from Arctic Canada show how rapidly the ocean rebounded. Within 2 million years, the number of marine species had doubled, marking one of the fastest recoveries in early Paleozoic history. The continents themselves were restless. Tectonic forces pushed Laurentia northward, while Baltica and Avalonia drifted toward it from the south, closing the Iapetus Ocean in a slow collision that would reshape the planet's geography. Along their converging edges rose the early Caledonian mountain ranges, ancient precursors to what would one day become the Scottish Highlands and parts of Scandinavia. These mountains, though nascent, influenced ocean circulation and weather systems, driving new currents that carried nutrients across shallow seas. Through these processes, the Earth's surface was being restructured, creating the geological scaffolding for future ecosystems. The climate during the early Silurian was a study in contrasts. The world had only recently escaped the grip of an ice age, yet warmth was returning swiftly. Marine sediments show signs of evaporite deposits, minerals like halite and gypsum indicating hot, arid zones along tropical margins. Elsewhere, black shales rich in organic carbon point to oxygen-poor waters, perhaps a lingering consequence of the extinction. Oceanic oxygen levels fluctuated sharply, alternately suffocating and feeding marine life. Yet through these cycles, the overall direction was upward towards stabilization, warmth, and habitability. By 435 million years ago, the Silurian world had reached a balance between ice and fire, a momentary peace in Earth's long battle for equilibrium. The chemical quiet of the oceans masked deep biochemical changes. As carbonate saturation increased, reefs began to reappear, first as small microbial mounds and then as complex coral stromatoporoid structures. These reefs became refuges for life, miniature ecosystems where recovery could take root. Early corals like favosites and halosites formed honeycomb and chain-like colonies, stabilizing seafloors and creating microhabitats for crustaceans, mollusks, and early fish. Stromatoporoids, sponge-like reef builders, layered calcium carbonate into domes that sometimes reached several meters in height. Fossilized remains of these structures, found in Gotland, Sweden, are so well preserved that geologists can reconstruct entire marine landscapes from them. In the shallower basins, chemical fingerprints tell another story. The ratio of strontium isotopes in marine carbonates shifted dramatically at the dawn of the Silurian, reflecting intensified weathering of continental rocks as ice melted and runoff increased. These weathering processes drew down atmospheric carbon dioxide, cooling the climate further and stabilizing the carbon cycle. It was a self-regulating feedback, the planet's first great experiment in long-term climate control. Modern geochemists see in these signals the early stirrings of the processes that would, millions of years later, make the planet's biosphere self-stabilizing, the faint beginnings of a planetary metabolism. While the surface world recovered, the deep sea harbored its own quiet revolution. Microbial life, though largely unseen in the fossil record, played a crucial role in resetting the planet's chemistry. Sulfate-reducing bacteria, thriving in low-oxygen sediments, recycled nutrients and metals that had been trapped during the extinction. Biomarker evidence from black shales reveals an increase in bacterial productivity during the early Silurian, an invisible pulse that preceded the visible resurgence of complex life. Evolution, it seems, always begins in the smallest places. By the mid-Silurian, roughly 430 million years ago, the outlines of a new world were visible. Oceans shimmered once more with planktonic life, and reefs stretched like emerald belts along the continental margins. The atmosphere, while still volatile, supported thicker ozone layers as oxygen levels climbed, protecting the surface from ultraviolet radiation. The stage was quietly being set for life to emerge from water to land, though that future remained hidden for now beneath waves and sediment. The Silurian world, fragile but vibrant, was Earth in recovery, a wounded planet rediscovering rhythm. And yet, in every trace of silt and shell, there was a sense of continuity. The same chemical cycles that had collapsed were now rebuilding themselves. The same forces that had extinguished life were crafting new forms of resilience. The oceans had stilled, but not forever. What appeared still at the surface masked gathering power below, slow, unseen, unstoppable. Soon, coral reefs would flourish again, armoured fish would rise from the depths, and the first roots of green life would clutch at the barren coasts. The age of renewal had begun, and from the silence of extinction, Earth was preparing to breathe once more. The rebirth of the oceans. At first, there was movement, faint at the edges, but steady. Where the waters of the Silurian had lain still, a subtle shimmer began to spread across the continental shelves. The sun, warmer now beneath a clearing sky, reached deeper into the sea, stirring dormant plankton back into their ancient dance. In the sediments, spores and cysts that had survived extinction awakened, releasing filaments and flagella into the light. Within a few million years, this microbial renewal transformed the chemistry of the oceans, enriching them with oxygen and nutrients. The world that had been stripped of colour was once again turning green and gold. Across the shallows of Laurentia and Baltica, coral and sponge colonies began to bloom in magnificent succession. Where the Ordovician reefs had fallen silent, small clusters of tabulate and rugose corals, favosites, halosites, heliolites, began to construct frameworks of calcium carbonate. Layer by layer, they built upward toward sunlight, cementing sand and silt into vast limestone ramparts. Fossil evidence from Gotland in Sweden reveals how swiftly these reefs spread. Within 2 million years, entire coastlines were fringed with stromatoporoid mounds, several meters high. These were not passive features. They were living metropolises, pulsating with invertebrates, algae, and the first symbiotic relationships that would later define coral reef ecology. Through shifting currents, plankton returned in swirling abundance. Phytoplankton, microscopic architects of oxygen, multiplied across the surface waters, their photosynthesis driving one of the largest primary productivity spikes of the Paleozoic. In their wake followed zooplankton, minute grazers and predators whose fossilized remains form the graptolite and chitinozoan assemblages, now used by paleontologists to map Silurian seas. Carbon isotope data from these microfossils reveal a steady increase in organic productivity during the Wenlock epoch, roughly 430 million years ago. The oceans were once again breathing, circulating, and sustaining layered networks of life that reached from surface to seafloor. From reef to reef, ecosystems expanded outward, each more intricate than the last. Stromatoporoid sponges stabilized the reef bases, corals built the middle walls, and crinoids and brachiopods anchored themselves to every available niche. Cephalopods, their conical shells glinting like ivory spears, hunted among the coral columns, feeding on trilobites that crept along the sand. In these shallow seas, energy flowed efficiently, a structured food web re-established from the ruins of extinction. Chemical traces from Silurian limestones, especially in the Yass Basin of Australia, show high ratios of strontium to calcium, a signal of active biomineralization and reef construction. In the dim pelagic depths, life found new shapes. Jawless fish, the ostracoderms, glided slowly through the murky water, their bodies encased in bone plates that shimmered under faint light. These ancient vertebrates, Cephalaspis, Tremataspis, and their kin, were evolutionary experiments in armor and endurance. Their bony exteriors protected them from predators and parasites, while sensory canals across their heads detected changes in current and pressure. Fossils from the Old Red Sandstone of Britain capture these creatures in remarkable detail, showing the early blueprints for vertebrate sensory systems that would later evolve into our own eyes and ears. The invention of bone itself marked a revolution biology had learned to turn chemistry into shield and structure. As the atmosphere steadied and temperatures rose, the ocean currents strengthened, carrying nutrients and larvae across greater distances. This circulation accelerated diversification. In reef margins, brachiopods and bryozoans colonized the spaces between coral heads, while trilobites adapted to new feeding behaviors. Fossil trackways in Silurian sediments from New York reveal complex burrowing patterns, evidence of specialized scavengers and sediment sifters. Even the once fragile graptolites, those drifting colonial organisms that had nearly vanished, reappeared in abundance, evolving into new branching forms that could filter food more efficiently. Life was not merely returning, it was refining itself. Within these waters, chemistry and biology formed a delicate alliance. The calcium carbonate saturation of Silurian oceans reached some of the highest levels in Paleozoic history, driven by intense continental weathering and the breakdown of volcanic rock. This abundance of dissolved minerals enabled rapid shell growth, thickening reef frameworks and stabilizing the seafloor. Oxygen isotope analysis from dolostone formations in the Canadian Arctic reveals stable sea temperatures averaging around 25 degrees Celsius, a warm equilibrium that persisted for millions of years. The Silurian world had become a planetary greenhouse, not in chaos, but in balance. Hidden under coral facades, microbial life performed its unseen work. Cyanobacteria and filamentous algae coated the surfaces of reefs, fixing carbon and forming biofilms that protected coral tissue from erosion. Stromatolites' ancient layered microbial structures returned in localized patches, particularly in hypersaline lagoons where larger animals could not survive. These microbial mats, though primitive, laid the groundwork for nutrient recycling systems that would one day sustain the complexity of modern reefs. Their chemical fingerprints, preserved as finely laminated carbonates, remind scientists that even the grandest ecosystems depend on the humblest engineers. By the close of the epoch, the Silurian seas had become vast engines of productivity. Carbon burial rates increased dramatically, reducing atmospheric CO2 and gradually cooling the planet. This biotic drawdown is recorded in the Wenlock-Ludlow boundary strata, where shifts in carbon isotopes reflect a pulse of organic sequestration unmatched since the Ordovician. The living ocean was now regulating climate. The biosphere had become a force of planetary engineering. As a result, atmospheric oxygen climbed towards 16%, laying the groundwork for future terrestrial colonization. Life had not only survived, it had begun to influence the very systems that once threatened its existence. In reef caves and shallow shelves, predators thrived. Nautiloid cephalopods, with jet propulsion and curved shells, patrolled the slopes. Eurypterids, massive sea scorpions reaching over 2 meters in length, stalked the shallows, preying on trilobites and early fish. This surge in predation drove new adaptations: thicker shells, faster mobility, and increasingly sophisticated sensory organs. The Silurian oceans had become arenas of competition and innovation, every creature a participant in the planet's evolutionary rehearsal. From this interplay of hunger and adaptation emerged the foundation of all modern marine food webs. At the planetary scale, the Silurian seas shimmered like liquid gardens. Coral reefs stretched thousands of kilometers, plankton clouds tinted the surface green, and armored fish glided through the currents like living relics of chemistry turned to form. The recovery was complete. The earth, once stripped bare, now pulsed with abundance. Each wave carried the residue of extinction and the promise of evolution, bound together in the rhythm of renewal. Beneath this vitality, however, subtle transformations were underway. Life was beginning to experiment with new ways of being: harder shells, sharper jaws, deeper senses. The oceans had healed, but they would not remain the same. What began as recovery was becoming reinvention, skeletons of survival. From the soft bodies of the Silurian bloom, life began once more to feel the weight of danger. The calm seas that had followed the Ordovician extinction were no longer silent. They pulsed with the presence of hunters. Small, jawed fish moved through the shallows with sudden precision, their cartilage skeletons flexible and efficient. What had been a world of drifting plankton and coral polyps now teemed with movement and pursuit. Flesh alone, soft and exposed, could no longer endure in waters where teeth had evolved. Evolution began to respond not in haste, but in chemistry. In the mineral-rich shallows, calcium and phosphate mingled freely within seawater newly oxygenated after the glaciations. As the Silurian oceans stabilized, the balance of ions shifted toward biomineralization. Organisms began to harness these minerals, precipitating crystals of hydroxyapatite, the same compound that would one day build human bones. What had been a passive chemistry of the environment became a tool of survival. In shell fragments and scale plates, the ocean's very elements began to rearrange themselves into armor. Across the continental margins of what is now Europe, North America, and China, the earliest armored vertebrates took form. These were the ostracoderms, jawless fish encased in heavy dermal bone. Their fossils, preserved in the Ludlow bone bed of England and the Wengan deposits of China, reveal intricate mosaics of bony plates fused over delicate bodies. Each microstructure was a masterpiece of evolutionary experimentation, dentine ridges interlocked with vascular canals, giving strength without brittleness. In these quiet seabeds, the skeleton became both fortress and fossil, a new language of endurance written in mineral. Within the ostracoderm's plated skulls, sensory canals traced fine lines beneath the bone, detecting faint vibrations in the water. These early lateral line systems allowed awareness even without sight, the beginning of a sensory sophistication that would later guide fish through the darkness of ancient seas. Beneath the plates, their internal cartilage scaffolding hinted at a hidden revolution. Some species, like Cephalaspis, developed flattened heads suited for gliding along the seafloor, using their armor as ballast. Protection and behavior were no longer separate. Form had begun to dictate function. Elsewhere in the Silurian seas, new forms of life echoed this mineral transformation. Placoderms, a newly emerging group of jawed fishes, appeared with interlocking head shields and bony thoracic plates. Fossils of Entelognathus from Yunnan, dated to around 423 million years ago, show the earliest known pattern of modern jawbones, precursors to the mandibles of all later vertebrates. Even arthropods and mollusks thickened their shells in parallel, evidence of a shared evolutionary pressure that spanned entire ecosystems. The ocean had entered its age of armor. Predators, sensing vulnerability, adapted in turn. Jawless hunters evolved flexible mouths rimmed with keratinous teeth, capable of scraping flesh and cracking shells. In response, the armored fish reinforced their plating, layering dentine with enamel-like substances. This cycle of adaptation became the Silurians' defining rhythm, each innovation answered by another, each defense met by new offense. The fossil record, scattered across ancient deltas, preserves this conversation in exquisite fragments. Teeth impressions etched into bone, microabrasions across fossil plates, mineralized wounds that never healed. Fossil evidence from Ludlow, Gotland, and Yunnan tells this story with clarity and scale. In Gotland's reef limestones, entire assemblages of armoured fish lie buried in ancient tidal channels, their interlocking plates still articulated. Geochemical analysis of these fossils reveals calcium to phosphorus ratios nearly identical to modern bone, a chemical continuity stretching 500 million years. In other sites, isotopic evidence from strontium and oxygen indicates that oceanic temperatures had stabilized near 30 degrees Celsius, warm, nutrient-rich waters, ideal for diversification. Life, once decimated, was now reassembling itself with purpose and precision. Through countless generations, bone shifted from surface armor to internal architecture. Dermal plating began to segment, to hinge, to accommodate motion. In some species, the earliest paired fins appeared fleshy protrusions supported by cartilage rods that would later become limbs. The skeleton, once a barrier, was evolving into a framework of movement. The chemical gift of calcium phosphate proved uniquely flexible. It allowed both rigidity and regrowth, structure and adaptation. The ocean's creatures were no longer merely armored. They were learning how to control their bodies with intention. Deep within the chemistry of bone lay another transformation, the regulation of life from within. The skeletal tissues began storing ions and buffering the body's internal pH, giving early vertebrates control over their internal environments for the first time. Genetic pathways that governed bone formation, analogues of modern RUNX2 and alkaline phosphatase, were switched on in these ancient lineages. The skeleton was becoming more than structure. It was physiology, a mineral organ through which life stabilized itself against the unpredictable sea. In the silence of those ancient reefs, the meaning of survival changed. The sea floor, once littered with soft-bodied remains, now held a diversity of mineral ghosts. Armor plates, scales, spines, and fragments of jawbone. Each fragment recorded not just the form of a creature, but the chemistry of its era. These bones told of a planet reawakening from ruin, experimenting with permanence, learning how to preserve memory in stone. The Earth itself had begun to evolve the idea of endurance matter, learning to resist decay through the language of bone. And so, from armor to motion, the story of life deepened. The skeletons that once confined movement would soon enable it. Fins would flex, muscles would anchor, and bones would become an instrument of freedom. Beneath the Silurian tides, evolution was preparing its next act, a world where survival no longer meant standing still, but learning to move, to hunt, to explore. In the shimmering quiet of those mineral seas, the first vertebrates carried the promise of transformation, and within their armor lay the seeds of motion itself. The pioneers of motion, from the armored quiet of the Silurian reefs, movement began as a whisper. The world had hardened in shell and bone, each life form a sculpture of endurance. But in that stillness, muscles began to coil beneath plates of cartilage. A pulse travelled through water, not yet a swim, not yet a chase, but the idea of motion itself. After eons of drifting and clinging, life was learning direction. In the dim shallows where sunlight fractured, shapes began to shimmer. Silt clouds twisted as bodies slipped free from the sea floor. Fins flickered like the flick of light through leaves, a soft translation of current into control. No longer prisoners of the tide, these early vertebrates felt the water push back and learned to push in return. With that resistance came balance, coordination, and intent. The ocean itself became a teacher. Here, the first true swimmers appeared descendants of jawless ancestors that had once fed by filtering mud. Among them, the early ostracoderms and anaspids flicked their tails with greater rhythm, drawing energy from segmented muscles called myomeres. In each contraction, evolution rehearsed a new idea: propulsion. These were not the fast, predatory fish of later ages, but quiet architects of possibility, fragile bodies testing the geometry of movement. Their arcs across the seabed were experiments written in flesh. With each controlled flick of fin and tail, life's dialogue with water deepened. Movement meant sensing, sensing meant awareness, and awareness meant survival. The first lateral line, system's delicate channels, etched along the flanks of early fish registered vibrations and turbulence. Through these silent signals, an organism could feel the approach of others long before sight evolved clarity. In a single innovation, space became perceivable. For the first time, life was not just in the environment, it was navigating through it. Anatomy became choreography. Pectoral fins began to spread like wings, paired and symmetrical. Pelvic fins followed, balancing thrust with stability. The evolution of these appendages marked one of the most profound revolutions in vertebrate history, granting control over roll, pitch, and yaw. Where once the ocean had carried its passengers, now the swimmers shaped its flow. The movement of water became an extension of will. Fossils from the Chengjiang and Ludlow strata reveal these transitions in exquisite detail. The Burkinia of Scotland, the Cephalaspis of ancient Welsh rivers, the Thelodus of Estonia, each bears traces of muscular articulation and fin folds that suggest experimentation. Sediment laminations around these fossils reveal current disruptions consistent with active swimming, not passive drift. These traces, subtle yet persistent, are the footprints of a revolution unseen by any eye, life claiming the third dimension of movement. The invention of paired fins changed everything. Energy could now be directed, not wasted. Bodies grew more streamlined, tapered at the tail, flattened at the head, a hydrodynamic architecture that turned resistance into momentum. By the late Silurian, the first placoderms, armoured fish with articulated jaws, appeared in reef margins. With jaws came pursuit, with pursuit came predation. The ocean, once a cradle of still grazers and filterers, transformed into a theatre of speed. Through this new symmetry of motion, the planet itself began to reorganize. Nutrient cycles shifted as predators redistributed biomass across depths. Coral ecosystems flourished under the turbulence of swimming schools, oxygenating waters, and stirring sediments. The balance of the sea was no longer maintained by chemistry alone, but by the kinetic exchange of life forms. Every flick of a fin altered the physics of survival. Predators followed the same path. The acanthodians, sometimes called spiny sharks, developed flexible bodies. Their fins braced with stiff spines that turned them into efficient hunters. They shared the seas with early chondrichthyans, precursors to sharks and rays, whose cartilaginous skeletons gave them agility unmatched by bone. In this age of innovation, speed was currency, and direction became destiny. Each improvement in motion rippled outward, forcing everything else to adapt or disappear. Within this living experiment of speed and precision, ecosystems evolved intelligence. Not the thinking kind, but a collective awareness, a choreography of prey and predator that balanced energy across the seas. The rhythm of pursuit and escape became the pulse of the planet. Where trilobites once crept and corals once fed passively, now the ocean sang with momentum. To move was to live. To hesitate was to vanish. By the close of the Silurian, motion had rewritten the rules of existence. Vertebrates had diversified into hundreds of forms, armoured, spined, jawed, or smooth, each a different interpretation of the same song of flow. Muscle bands deepened, tails forked, and fins refined into precise instruments of control. In ancient reef deposits, trails of feeding marks trace zigzag paths, showing how movement had become behaviour. The sea was no longer static. It was a map of intentions. And in that final shimmer of water and light, a new quiet took hold. The rush of fins slowed. Above the shallows, the air trembled with change, sunlight stronger, currents warmer, coasts thickening with silt and decay. Motion had reshaped the sea, now it would reshape the shore. Along the edges of continents, spores floated on the wind, settling among wet stones and tidal pools. Life, having conquered depth and direction, was preparing to conquer height. The water stilled again, but it was not the same silence that came before. Ripples carried memory, each wave a record of motion. Beneath them, the pioneers of swimming carved their legacy into the planet's design. And as those ripples faded toward land, the first green threads reached upward, drawn by light, moved by the same invisible pull that once taught fins to flicker. The green frontier. From the rippling shallows where fins once flickered, the world held its breath. The water's edge shimmered beneath a pale Silurian sun, the air dense with vapour and silence. Waves collapsed onto mudflats, glazed with salt, where nothing yet claimed the space between sea and sky. For hundreds of millions of years, land had been nothing but theatre, an empty stage of stone, wind, and occasional rain. But something invisible had changed. The seas, rich now with oxygen and nutrients from ancient reefs, had begun to whisper to the shore, and in those whispers lay the promise of green. Above the tide line, silence reigned. The continents, Laurentia, Baltica, Gondwana, were bare and ochre, their surfaces cracked from endless exposure. No grass softened their edges, no roots clung to their slopes. Dust storms crossed the empty plains, where tectonic collisions had begun to raise mountains. And yet, on certain coastal flats, where moisture lingered and tides reached far inland, life began its most fragile experiment, to exist beyond water's embrace. What first crept from the shallows was not an animal, but a thread, a film of photosynthetic filaments that glistened briefly before drying under the sun. The first greenery was not forest, but filament microscopic chains of cells related to modern algae, testing survival in a desolate new world. These pioneers clung to thin films of water that gathered after each tide, capturing sunlight and carbon through primitive pigments. Their remains, preserved in ancient sediment, formed dark streaks in Silurian shale, some of the earliest hints that photosynthesis had crossed the shore. It was a beginning so small that no eye could have noticed it, yet within these fragile mats lay the chemistry that would one day change the air itself. Rhiniophytes and Cooksonia rose only centimetres high, but their appearance marked a revolution. Fossil imprints from the Rhynie chert of Scotland reveal slender stems, smooth and branching, each tipped with a sporangium, a vessel for spores. These were the first true vascular plants, their tissues specialised to move water and nutrients upward, defying gravity's claim. In the warm, humid air of the Silurian, they formed delicate thickets along the edges of pools, binding the mud beneath them. In those clusters, evolution took root not through size, but through circulation. Through these stems flowed something entirely new, a vascular pulse. Inside the thin walls of these plants, early xylem and phloem ferried life's fluids in opposite directions, one carrying water and minerals from the earth, the other sugars from the sunlit tips. This dual system allowed plants to rise higher, to hold their bodies above the surface film of moisture. It was a mechanical breakthrough as profound as the evolution of fins. For the first time, life could channel energy vertically, lifting itself into the air. With each generation, roots dug deeper into mud once sterile. Simple rhizoids became branching anchors, trapping silt and clay against the pull of rain. The texture of the land began to change. Loose sediments compacted into protosoils, darkened by decaying organic matter. Chemical weathering intensified as roots exuded acids that broke down rock into mineral nutrients. In laboratory reconstructions, these biological reactions, are measured in shifts of only micromoles per gram, but across a continent, they rewrote the chemistry of the surface world. Soils began to form, and they're not just layers of sediment, but living systems, dynamic interfaces between rock, air, and life. Modern analyses of Silurian deposits show the first evidence of humic compounds, the molecular fingerprints of decay. These substances, rich in carbon and nitrogen, represent the beginning of terrestrial nutrient cycles. What had once been sterile was now fertile, and with fertility came permanence, a landscape that could retain water, support growth, and resist erosion. Chemical signatures in Silurian strata record this transformation. In rocks from Wales, Estonia, and China, shifts in isotopic ratios of carbon and oxygen mark a slow decline in atmospheric CO2, a signal of photosynthesis expanding across new terrain. The planet's breath was changing, carbon locked into soil, while oxygen seeped into the atmosphere, its rising concentration measurable in trapped bubbles of later Devonian amber and marine proxies. The Earth's air, once thick with volcanic gases, was becoming breathable. As plants breathed, the atmosphere changed. The greenhouse haze that had long trapped heat began to thin, cloud patterns shifted, rain fell more regularly, and surface temperatures cooled by degrees that reshaped global circulation. Studies of Silurian climate models suggest a reduction of up to 15% in carbon dioxide over several million years, enough to stabilize sea levels and foster new coastal ecosystems. The land, once sculpted only by physics, was now under the influence of biology. Carbon dioxide fell, oxygen climbed, climate patterns shifted, the feedback deepened. With every root and rhizome, erosion slowed. Rivers meandered instead of scouring. Sediment began to accumulate in deltas where microbial life flourished anew. The transformation was not sudden but cumulative, recorded in millimetre-thin bands of mudstone that span eons. Each layer a testimony to persistence. Each mineral grain a record of life's patient engineering. The planet's surface, once scoured by wind, began to hold itself together. Green patches spread where spores are found. Over time, these pioneer plants diversified, some forming primitive leaves to capture more light, others developing thicker cuticles to withstand dry spells. In their wake came fungi, forming symbiotic partnerships that enhanced nutrient exchange. This union between root and fungus, the earliest mycorrhizal relationship, became the hidden architecture of land life. Beneath every patch of greenery, threads of fungal hyphae intertwined with roots, expanding reach and resilience. At the edges of this new world, the boundary between sea and land softened. Marshes thickened into low mats of vegetation, their remains forming the first peat deposits. Insects and arthropods from nearby tidal zones began to explore these stable surfaces, feeding on decaying matter and spores. The landscape no longer belonged solely to geology, it belonged to life. In time, the rustle of tiny stems would become the murmur of forests. But for now, the transformation was quiet, measured in inches and centuries, not storms. The air smelled faintly of wet stone and decay. Raindrops darkened the soil, and the first true leaf unfurled against the wind. Above it, sunlight fractured through a thinner, clearer sky. Somewhere in the shallows nearby, a ripple broke the surface, the memory of motion still alive beneath the water. Onshore, the wind lifted a cloud of spores, carrying them toward distant shores. The world was learning to breathe, and with that breath came permanence, and as the light faded, the green frontier expanded slow, deliberate, unstoppable turning dust into habitat and silence into song. The earth, once sculpted by seas, now began to sculpt itself anew. The architects of land. A hidden alliance began to stir as the first carpets of greenery spread across the land. Beneath the fragile stems and creeping mats of early plants, something ancient and unseen began to weave the land together. Threads of fungus stretched through the soil, binding mineral to moisture, rock to root. The earth's surface, once raw and eroding, began to breathe differently. It was not a loud transformation, but a slow whisper of chemistry and cooperation, an alchemy of stone learning to live. In the dim humidity of the Devonian dawn, spores drifted like dust, settling into the pores of stone. They found partners weighting the roots of primitive vascular plants, tentative and slender, barely able to anchor against wind or flood. Between them formed a dialogue written in carbon and phosphorus, exchanged through filaments finer than silk. These were the mycorrhizal unions, the earliest microbial marriages of necessity. Through this quiet trade of nutrients and energy, the surface world gained stability. Soil, true, living soil, was born. Across floodplains and tidal flats, this unseen web expanded. Fungal hyphae reached deep into crumbling sediments, drawing water and metals, feeding the plants that reached for air. Every root became an anchor point, every thread a vein in the growing body of the land. Together, they slowed erosion, captured sediments, and locked carbon into the ground. The bare crust of continents softened beneath their touch, turning from desolation into texture, from stone into substrate. Where mosses met the fungi, small colonies of lichens formed symbiotic mosaics capable of colonizing the harshest rock. Their acids etched into stone, releasing elements essential for plant life. Over generations, this biochemical weathering sculpted the first protosoils, thin, fragile layers, rich enough to sustain vegetation. The landscape itself became an organism in slow motion, eroding, feeding, and rebuilding in an endless cycle of decay and renewal. Each rainfall brought nutrients from the sky. Each dry spell left mineral ghosts behind. Within this microscopic architecture, fungi became engineers of vast consequence. Some species formed dense networks known as mycelial mats, capable of transferring signals and nutrients between distant plants. These early wood-wide webs predated the trees they would one day serve. In their lattice of filaments, the foundations of ecological intelligence emerged not in brains, but in flows of carbon and connection. The land was learning to communicate, one chemical pulse at a time. Evidence of this hidden world survives in the fossil record fragments of arbuscular mycorrhizae, preserved in 400 million-year-old chert from Rhynie, Scotland. Under microscopes, their delicate branching structures still reveal the same mutual embrace seen in modern forests. Isotopic analyses confirm that these partnerships accelerated mineral weathering and atmospheric stabilization. In essence, fungi helped set the stage for the planet's next climate balance, reducing carbon dioxide through enhanced rock decay and feeding the greenery that further cooled the world. The expansion of roots and hyphae also changed the color of the earth. Iron oxidized, clays formed, and sedimentary layers thickened into red beds. Rivers began to meander instead of rushing straight to the sea, their banks now reinforced by vegetation. What had once been barren floodplains became mosaics of plant cover, fungal crusts, and microbial life. Each patch of soil became a miniature cosmos of exchange, a network of decomposers, builders, and regulators. As these systems deepened, new biological feedbacks arose. Soils trap organic matter and release oxygen into the atmosphere, aerobic microbes flourished, accelerating decay and nutrient cycling. The world's chemistry tipped toward vitality, creating conditions that would one day sustain forests and animals alike. For the first time, land was not merely the life stage. It was a living system in its own right, a dynamic equilibrium between rock and respiration. Out of this teeming substrate, evolution diversified its architects. Early fungi like prototaxites towered over the landscape, massive trunk-like forms rising to 8 meters high. For centuries, scientists debated their identity: giant algae, lichens, or fungi. The evidence points to fungal giants decomposers that dominated before true trees appeared. They recycled nutrients from dying plants, fueling the next wave of vegetation. In their strange bulk, one can glimpse the Earth's first vertical structures, built not of wood, but of woven filaments. Meanwhile, root systems of early plants, such as Asteroxylon and Aglaophyton, burrowed deeper, stabilizing slopes and altering water flow. Their presence reshaped entire watersheds, changing how rainfall carved the land. Geochemical traces from ancient soils, paleosols, reveal rising levels of organic carbon and clay minerals, hallmarks of sustained biological weathering. Through these gradual interactions, continents became more than surfaces. They became metabolisms. With each passing epoch, the collaboration between fungi and plants grew more intricate. Nutrients circulated in loops rather than linear decay. Death became raw material for new life. Every fallen stem fed 1,000 roots. Every decayed fungus seeded a fresh network. It was an invisible architecture of renewal, building the foundation upon which insects, amphibians, and forests would later depend. For all its calm, beyond this flourishing stillness, something waited. The mossy flats now teemed with spores, invertebrates, and detritus. Air shimmered with oxygen, once trapped beneath waves. The land was ready for movement. Its scaffolding is complete, its breath balanced. It calls for new architects, creatures not of root or thread, but of limb and exoskeleton. Between the roots of ferns and the columns of fungus, tiny pioneers began to stir arthropods and millipedes, tracing cautious paths across damp ground. Each step left an impression, shallow and uncertain, but profound. The world that had once relied on diffusion and drift was now opening to motion and migration. And as the light filtered through the first canopies of green, the silence of the land broke again, this time with footsteps. The crawlers of the shore, light fractures on wet stone, scattering into 1,000 tiny signals that the first terrestrial explorers would learn to read. At low tide, sunlight skitters across pools and slick mud, refracting through ripples like shattered glass. This was no longer the diffuse glow of subaquatic light, but a sharp, directional blaze, a challenge to eyes evolved for the sea. Compound lenses adjusted, pigments darkened, and movement took on a new precision guided by shadow and shimmer. Along ancient tidal flats, animals paused beneath this unfamiliar brilliance, recalibrating orientation and behavior. For the first time, perception extended beyond the reach of water. Tremors ripple through the shallows, carrying information more ancient than sight. Vibrations transmitted through wet sand and thin films of retreating tidewater spoke of pressure, pursuit, and approaching waves. Early arthropods were masters of this hidden sense, their bodies lined with delicate setae and hair-like sensilla that could register the smallest quiver. A distant breaker or a shifting crab became not just a sound, but a texture felt along the limb. The shore was both signal and trap, a vibrating network that trained life to listen to the planet's pulse even as it dared to cross its boundaries. Shells grind softly against one another, a language of friction and endurance. Their ridged surfaces, calcium, sulfate and chitin, bound into intricate plates, scraped over rock polished by centuries of tides. Many of these exoskeletons still bore hydrodynamic traces, grooves that once split currents, now etched against rough terrain. Fossils show worn edges, scratches angled upward as though from repeated efforts to climb or drag across stone. Every abrasion marks a negotiation with gravity, each polished scar a testament to trial by contact. To move on land was to remake the body's contract with matter. Creatures hesitate, then press forward, testing weight and balance in a realm that offers no buoyant mercy. Limbs once evolved for swimming, reoriented into tools of propulsion and restraint. The first millipede-like arthropods extended their segmented bodies, like bridges across micropools, distributing their weight through coordinated waves of motion. Trace fossils from sites such as the Cowie Formation in Scotland and the Tumbler-Gouda Sandstone of Australia reveal alternating patterns of contact and lift the imprint of hesitation turned into momentum. Each trackway tells of experimentation as instinct discovered the geometry of stride. Muscles coil beneath translucent armour, storing potential energy in rhythmic contractions. Within those segments, myomeres, once used for undulating thrust, now became engines of leverage. Internal attachment scars in early terrestrial arthropods show reinforcement at limb bases, evidence of mechanical adaptation to gravitational strain. The coordination of antagonistic muscle pairs allowed limbs to lift, plant, and recover the earliest biomechanics of a step. Through these hidden structures, motion acquired purpose, and the architecture of walking took shape one evolutionary improvisation at a time. Moist air clings to jointed limbs, a new element demanding innovation. Water loss threatened to undo every terrestrial experiment. In response, exoskeletons thickened, fine waxes coated surfaces, and the first primitive spiracles appeared as tiny perforations leading to internal air channels. Fossil evidence from Silurian eurypterids and early myriapods shows hints of these dual respiratory systems' gills modified into air-breathing lamellae or tracheal folds. With each adjustment, the impossible seemed slightly more survivable. Land was no longer a barrier, it was an unfinished invitation. Tracks appear where no tide reaches, faint yet deliberate in their spacing. The sediment that captured them, fine-grained, laminated, sometimes cross-bedded, speaks of transient dryness and the brief stillness between floods. Each impression records not only anatomy but timing, pauses that correspond to rest, parallel lines where a body dragged forward, splayed claws marking a stumble. Some of these traces run parallel to algal mats, hinting at early cooperation between organism and substrate life, using life as scaffolding. In these markings, paleontologists read the first diaries of terrestrial motion. Scavengers follow scent and vibration, bridging the worlds of water and air in short, efficient cycles. Detritivores exploited decaying seaweed, fish remains, and microbial films that clung to the shore. Isotopic analyses from fossilized organic residues reveal gradients of delta-1,3C values that trace the mingling of marine and terrestrial carbon sources to the earliest blurring of ecological lines. Predators soon followed, drawn by chemical cues rather than currents. Every interaction here, feeding, retreating, returning, helped stabilize the threshold ecosystem, transforming the tide line into a living laboratory. Ancient winds lift the smell of decay and salt, carrying with them light spores and minute arthropods across damp flats. This invisible current functioned as both hazard and opportunity. Desiccation for the unprepared, dispersal for the fortunate. Some early land pioneers used behavior as adaptation, burrowing under damp debris, hiding beneath stones, or timing their excursions to the cool of the evening. Climate reconstructions from evaporite sequences show fluctuating humidity patterns that mirrored these behavioral rhythms. Even at this stage, evolution had begun to synchronize physiology with the atmosphere. Movement becomes memory etched in stone, each fossil a frozen improvisation. The trackways, molted shells, and tiny burrows together narrate a slow mastery of a new dimension. Over thousands of generations, what began as brief crossings lengthened into seasonal habits, then permanent colonization. The interface between land and sea blurred into continuity, and ecosystems layered upon one another in complex interdependence. What had been the edge of survival became the foundation of expansion. Shadows stretch along the retreating tide, silhouettes of creatures now fully capable of traversing the divide. In that twilight zone of wet sand and glimmering rock, the crawling multitudes laid the groundwork for terrestrial ecosystems yet to come. As plants deepened their roots and fungi spread their networks, these animals recycled decay, oxygenated soil, and built the first stable nutrient loops on land. Their steps echoed beyond their weight, setting the tempo for all who would follow. And as night gathers across the tidal plain, the air hums with the residue of motion, faint, rhythmic, continuous. The last ripples fade and silence returns, but the pattern has changed forever. Life has learned to stretch between two mediums, to breathe both water and air, to test boundaries and make them porous. Above the darkening surface, the wind carries the scent of growth from distant marshes where green thickens and roots bind earth to itself. The shore has given up its secrets. Now the land begins to weave them into form, reefs of wonder. Down through the blue haze, the sea folds over itself in layers of colour and motion. What was once a barren seafloor has become a cathedral of life, an underwater sprawl where silence hums with energy. The Silurian seas are calmer now than the violent epochs before. Volcanic fury has quieted, continents drift in slow grace, and sunlight penetrates through crystal shallows to ignite the work of life. Here, existence no longer clings, it constructs. The reef begins as a whisper, a fragile colony of corals anchored to stone. They do not move, yet their stillness is a kind of labour, an act of collective creation that will reshape oceans and, in time, the very chemistry of air. Under the spill of fractured light, colour becomes architecture. Polyp by polyp, tiny builders secrete calcium carbonate, layering their lives into pillars and domes. Stromatoporoid sponge-like creatures with mineral skins join the effort, adding weight and form. Together they weave fortresses that shimmer beneath tides, walls of living stone rising toward the sun. Plankton swirl through corridors of coral branches, larvae drift in slow spirals, and the water thrums with unending motion. This is no passive ecosystem. It is a city in progress, alive, humming, layered with purpose. Within its alcoves, early fish find shelter. Between its towers, trilobites patrol, their shells gleaming as they scavenge detritus from the coral streets. Every crevice hides a story of survival, competition, and connection. Layer upon layer, the reef constructs itself, as though guided by an unseen geometry. Each coral generation dies and leaves a foundation for the next, a rhythm of birth, death, and renewal that builds cathedrals over time. These reef systems stretch for hundreds of kilometres along continental margins, from the edges of Laurentia to the shadows of Gondwana. They become living shorelines, stabilising currents and filtering sediment, and in their slow persistence, they accomplish something profound. They fuse life and geology. For the first time, Organisms are not merely moulded by the planet, they begin to mould it in return. Stone learns softness, flesh learns permanence, boundaries dissolve. Cyanobacteria nestle within coral tissue, sharing sugars born of sunlight in an ancient act of reciprocity. Algae feed the coral. The coral gives them shelter and carbon dioxide. It is a symbiosis that will echo through all of Earth's future, a prototype of the alliances that sustain forests, fungi, and eventually entire planets. Inside this cooperation, we find the blueprint for stability in an unstable world. Around them, the first jawed fish glide with newfound elegance, adapting fins for precision rather than flight. Evolution refines detail by detail, sharpening both beauty and strategy in these coral labyrinths. In the shimmer of these reefs, chemistry becomes choreography. Each coral polyp extracts dissolved ions from seawater, transforming them into crystal lattices that harden into stone. Through this process, calcification carbon is locked away for ages, stored in the reef's expanding skeleton. What seems decorative becomes geochemical, a mechanism that lowers carbon dioxide in the oceans and cools the global climate. The reef, radiant in colour and form, acts as one of Earth's earliest climate regulators. Its beauty carries consequence. Its architecture becomes an atmosphere. Across epochs of calm and catastrophe, the reef endures. Warm periods ignite bursts of coral growth, while colder ages strip the shallows bare. When glacial cycles lower the seas, entire reef systems stand exposed, bleached, and lifeless beneath an alien sky. Yet even death becomes design. The exposed reefs turn to limestone, compacted under the weight of time, preserving the fingerprints of countless generations. Within those stones now lifted high in mountain belts or sliced open by quarries, paleontologists read the codes of ancient oceans. Trace elements, oxygen isotopes, and chemical ratios that tell stories of warmth, oxygenation, and the pace of planetary change. In these fossilized reefs, we glimpse not only the creatures that built them, but the chemistry of life itself written into stone. The balance between carbonate and magnesium, the faint presence of strontium, these are the archives of ocean temperature and acidity. Scientists can track how shifts in atmospheric oxygen and volcanic outgassing left signatures across the seafloor. Coral skeletons, in their crystalline order, hold data that modern instruments still struggle to match. They are instruments of memory, instruments that remember far beyond the scale of species or civilizations. The Silurian sea glows in silence, and within it the reef awakens not structure but pulse. Each polyp reacts to the rhythm of waves, contracting at night, feeding with the dawn. Predator fish prowl the outer edges, while armoured eurypterids glide along the reef's base like shadows of the deep. Sponges filter water in continuous flow, and tiny crustaceans perform the endless labour of cleaning, scavenging, and balancing the system. The coral reef is not a single organism, but a choreography of thousands, each moving to sustain the whole. In its balance of creation and decay, it mirrors the metabolism of the planet itself. When sunlight dims and the tides turn colder, many of these coral cities collapse. Climate pulses or volcanic events poison the water, and entire reef belts vanish from the fossil record. Yet this loss is not the end. New reefs will rise in other oceans, formed by other builders, a lineage of architects that will persist for hundreds of millions of years. From Silurian to Devonian, from Cambrian ancestors to modern coral atolls, the pattern of life's architecture continues. The urge to build, to stabilize, to endure. Even extinction becomes a kind of renovation, clearing space for the next iteration of the reef's grand experiment. The beauty of reefs belies their reach. They sculpt marine life, and alter the geological fate of continents. As sediments accumulate around their foundations, they stabilize shelves, create natural barriers, and direct ocean currents. Over geological time, these formations will uplift into mountain chains, feeding future soils with calcium and carbon. Entire ecosystems, terrestrial and marine alike, will owe their chemistry to these silent builders of the sea. In this sense, the reef is not only the heart of an oceanic world, but the scaffolding of future Earth. While reefs blazed with life, the next transformation gathered quietly offshore. The planet's systems, once operating in isolation, are starting to converge. Oxygen from the sea feeds the air, minerals from the land enrich the shallows, life from one realm begins to influence another. Beneath the surface, the reefs hum with stability above it. The world prepares for change. Soon, the focus of creation will shift again, from coral spires to continents breathing anew. The story of life will rise from water to wind, the planet that learned to breathe. Above the coral seas, the light changed. The ocean, once ruler of all life, gave way to the glimmer of damp shorelines. Here, the air hung heavy, not yet a home, but a frontier. From shallow pools and tidal flats, green threads of algae extended into the open, clinging to silt and stone. Each step beyond the waterline was a negotiation with desiccation, radiation, and gravity. Yet within that struggle began a quiet revolution. Life learning to speak the language of air. Air, once thin and inert, began to carry life. The atmosphere, still thick with carbon dioxide and thin on oxygen, shimmered above these first colonists. Simple mats of liverwort-like plants formed on moist soil, capturing sunlight through primitive chloroplasts. Every photon they trapped became a spark of chemistry, splitting water, releasing oxygen, and binding carbon into matter. The world's first breath was not a storm, but a whisper rising from moss and mud. Tiny vascular plants crept inland, armed with the earliest xylem and phloem channels that moved water upward and sugars downward, creating the pressure systems that would one day support forests. Cooksonia appeared in the fossil record as a simple, leafless stem branching at its tip, but its internal scaffolding marked a threshold. For the first time, life had the architecture to stand above the surface, to meet wind and light head-on. In the wet air of the Silurian, evolution found a new direction, vertical. Each leaf was an experiment in atmosphere. Cuticles thickened to guard against evaporation. Stomata evolved to open and close tiny lungs embedded in plant skin, regulating the trade between air and life. With every cycle of sunlight, these microvalves exhaled oxygen, a gas that would soon accumulate across continents. In the chemistry of these cells lies the first hint of balance, photosynthesis and respiration, opposing currents bound in a single rhythm. Through photosynthesis, a revolution began. The reaction itself was simple. Carbon dioxide and water made sugar and oxygen, but its consequence was planetary. Each molecule of carbon, fixed into biomass, was one removed from the air, cooling the planet molecule by molecule. Geochemical records, locked in ancient carbonates, preserve this signature. A steady enrichment of carbon-13, proof of massive carbon drawdown by expanding vegetation. Carbon levels plummeted as plants captured sunlight's excess. What had once trapped heat in the lower atmosphere now sank into soils and sediments. Radiative models of Silurian Devonian climate suggest that CO2 levels fell from more than 6,000 parts per million to below 3,000, initiating a global cooling trend. The sun's warmth met new resistance, filtered through leaves, absorbed by photosynthetic surfaces, and redistributed by the planet's widening canopy of green. Sediment isotopes reveal the breadth of this new biosphere. Layers of weathered rock and ancient red beds speak of oxygen's rise. Iron, once dissolved freely in anoxic waters, is now oxidized into rust, painting the continents in streaks of ochre and crimson. Atmospheric oxygen approached 15%, enough to sustain the slow-burning chemistry of respiration and to awaken fire itself. Where lightning struck dry peat, flame danced for the first time across a living earth. Oxygen accumulation reshaped not only air, but fire. Combustion, once impossible, became a regulator of life. Too little oxygen and the flame dies, too much and the planet burns. The biosphere, through its own exuberance, had to learn restraint. Charcoal deposits from Devonian strata testify to this delicate equilibrium, evidence that forests and atmosphere negotiated a new kind of balance, an ecosystem aware of its own volatility. Weather patterns shifted as forests deepened. Vegetation drew moisture upward and released it skyward in plumes of transpiration. Clouds formed inland, carrying rain far from the sea. The hydrologic cycle became continental, no longer confined to coastlines. With every storm, soil eroded and rivers changed course, delivering nutrients back to the ocean. Life was no longer a passenger on Earth's systems. It had become an engine. The Earth's skin thickened with green, and the planet cooled. Expanding forests captured carbon faster than volcanoes could release it. Global temperatures dropped, glaciers spread once more across Gondwana, and sea levels fell. The biosphere had altered planetary albedo. Sunlight reflected differently off forests than off bare rock. Even the winds shifted, sculpted by new temperature gradients between vegetated land and open sea. This transformation had an intelligence of its own. Feedback upon feedback, process upon process, each reinforcing or balancing another. The roots of plants accelerated the weathering of silicate rocks, pulling carbon dioxide into solution and burying it as carbonate sediment. Soil microbes evolved to recycle nutrients, linking atmosphere to geology through biology. Without intention, the planet behaved as if it were self-aware, a system sensing its own breath. In this balance of breath and stone, Earth entered a new phase of stability. Oxygen, carbon, and water began to cycle in rhythms that would sustain complex ecosystems for hundreds of millions of years. Fossil spores preserved in ancient mudstone reveal how far these green empires reached across floodplains, deltas, and inland basins. The biosphere, once confined to shallow seas, had wrapped the continents in a living fabric. At the close of the Silurian, the planet exhaled stability for now. In the following Devonian dawn, ferns and early trees rose skyward, their roots penetrating deeper into rock, their shadows longer across the land. With each season, their decay enriched the soil and drew yet more carbon from the air. Oxygen levels climbed again, inching toward the threshold that would allow animal lungs to evolve. Far beyond the horizon, rivers cut deeper, preparing for what comes next. The sediments they carried bore the record of life's newest transformation, carbon bound into roots, oxygen bound into sky. The earth had learned to breathe, and in doing so, had changed the meaning of life itself. From invisible chemistry to visible consequence, the surface reshaped under its own creation. The seas cooled, the forests whispered, and somewhere within that steady rhythm of breath, the next revolution stirred. Continents in motion. Under the weight of continents, the planet stirred again. Deep below the surface, the crust, once quiet and fractured, began to shift under forces that had never truly slept. Faults stretched like old scars reopening, while molten rock moved restlessly in the mantle, carrying the planet's stored heat upward in silent revolutions. The stillness of the surface masked an orchestra of movement below one that tuned itself not to seconds, but to ages. Vast chambers of heat began to flex and fold, testing the crust's resolve. In the unseen darkness, convection cells churned, their rising plumes driving the tectonic dance. What seemed fixed on the surface was, in truth, an elaborate negotiation of stone, the planet balancing energy and structure, creation and destruction. Every continent, every ocean floor became a participant in this vast exchange between gravity and fire, between the solidity of rock and the fluidity of time itself. Continental plates, adrift on molten currents, resumed their slow migration, 1 inch toward another, drawn by ancient heat gradients and the pull of subduction zones. Oceans closed, trenches deepened, and the planet's surface folded like fabric under invisible hands. These movements, imperceptible on human timescales, shaped entire worlds over millions of years, raising mountains, splitting basins, and redrawing the geography of life. Where slabs converged, oceans vanished, and stone rose in defiance. Mountain chains erupted from the wounds of collision ridges that tore through the horizon, born of compression and uplift. What had once been seabed became sky, coral limestone metamorphosed into marble, and sediments hardened into chronicles of buried time. Each summit, raw and unweathered, marked an upheaval that would redirect rivers and rewrite climates. Valleys deepened in their shadows, and the first winds that passed over them carried the taste of minerals newly exposed to the air. Geologists later traced these collisions in seams of deformed granite and gneiss. These metamorphic relics hold the memory of pressure crystals realigned under temperatures so high that rock flowed like wax, yet somehow survived to tell the story. Through them, the sequence of Earth's collisions could be reconstructed, piece by tectonic piece, revealing that even the hardest stone remembers its past. The Caledonian, the Akkadian, the first shadows of the Appalachians all spoke of pressure made permanent. These were not isolated events, but linked convulsions, the choreography of an assembling supercontinent. Fragments that once drifted freely, Laurentia, Baltica, Avalonia, met along fiery sutures to form a new terrestrial unity. From these continental unions, new highlands rose, and with them, new weathers. Across vast latitudes, atmospheric circulation reorganized, shifting the paths of storms and setting the stage for climatic transformations yet to come. Basins collapsed as continents locked together, sealing the memory of ancient seas. In their place, shallow inland waters formed, ephemeral and rich, with sediments eroded from young mountains. These temporary seas became crucibles of evolution, their fluctuating coastlines breeding diversity. What was once the ocean floor now held forests, while distant shallows dried into plains that awaited the first explorers of air. The earth was already hinting at what it would someday host creatures that could cross from water to land, tracing the boundaries written by geology itself. Mineral isotopes record this era as one of fire, water, and relentless compression. Strontium and neodymium ratios in marine rocks reveal surges of continental erosion, while oxygen isotopes in quartz tell of rainfall heavy with the scent of new mountains. Even the carbon buried in ancient floodplains carries the fingerprint of uplift, a planetary feedback between land formation, climate, and life. In this interplay, the continents became more than inert masses. They became regulators, architects of their own atmosphere. Volcanic arcs ignited where the crust tore itself apart. Each eruption sent ash into the sky and minerals into the sea, fertilizing distant ecosystems. Lava solidified into basaltic plateaus, that would one day cradle forests. Pyroclastic flows erased landscapes as quickly as they formed. Yet from their ashes, new environments took shape. In every direction, geology and biology intertwined. The breathing planet feeding its surface with fire, while life in turn shaped its erosion and renewal. New mountain chains redefined the sky, bending weather and rewriting wind. As peaks rose, they intercepted moist air, birthing monsoons and desert shadows. The planet's climate, once largely governed by oceans, began to feel the dominance of land. Airflow patterns shifted, polar ice advanced, and rainfall sculpted river systems that would persist for hundreds of millions of years. Storms became sculptors, carving the faces of mountains and feeding the sedimentary basins that would archive their own origins. Rainfall carved young slopes, feeding rivers that carried the planet's waste to sea. Sediment-filled basins bury organic matter that would become coal and shale. The carbon drawn from air and life found refuge beneath rock, another layer in Earth's long cycle of respiration. Rivers became both veins and memory, linking mountain to delta, deep time to present motion. Through these channels, the living and the lifeless traded places. Carbon from air to stone, stone to soil, soil to seed. Forests adapted to altitude, and ecosystems reshaped around the contours of uplift. Plants learned to anchor in thinner soils, their roots prying into cracks of granite. The expansion of vegetation on mountain flanks accelerated weathering, drawing yet more carbon from the atmosphere. In these highlands, life and lithosphere forged a new kind of dialogue, each shaping the other in the slow language of feedback. As mountain roots deepened, biological roots followed two forms of persistence, one geologic, one alive. After each collision, silence followed the long exhale of erosion and time. Peaks weathered to plains, sediments washed away the evidence of upheaval, and the planet rested before its next breath. Yet even that rest was temporary. Beneath the cooling crust, mantle plumes reorganized, currents shifted, and the next cycle began to stir. The Earth, even in stillness, was never still. From crustal fracture to continental fusion, the planet rehearsed its ancient rhythm. Each movement served a purpose: to redistribute heat, recycle minerals, and renew the face of the world. The continents themselves became instruments of planetary balance. Over eons, their collisions formed the framework for ecosystems to expand, for climates to stabilize, and for evolution to explore every possible niche. Over the young mountain spines, life waited, sensing its next becoming. The landscape was changing again, not from chemistry or climate alone, but from the architecture of the planet itself. What began as continental drift would soon dictate destiny. Rivers carved deeper, valleys widened, and new environments beckoned. The next story would not be written in stone, but in the creatures that learned to follow it, predators of a new world. In the calm that followed the collision, life grew bold. With the planet's geography stabilizing and ecosystems filling the niches carved by mountains and rivers, organisms seized the chance to specialize. Small opportunists became hunters, scavengers became specialists. The stage set by continents in motion now hosted an intensifying drama, one where speed, senses, and force determined the winners. Predation began as an accident of opportunity. A stranded carcass, a dense plankton bloom, the gap between a hiding place and an exposed flank, these moments offered the first chances for aggression to be rewarded. Natural selection amplified crude advantages. A sharper spine, a slightly faster lunge, a jaw that could clamp rather than sift. Over generations, accidental advantage became engineered design. From the murk of Silurian seas, shadows began to move. Long silhouettes carved the water, bodies built for power. Broad tails for thrust, streamlined exoskeletons for cutting through current, and jointed limbs that doubled as weapons. The dim shallows, once populated mainly by filterers and grazers, now echoed with pursuit. Prey species shifted behavior and form in response a feedback loop of pressure and counterpressure that sharpened both predator and prey like a whetstone. Armoured forms patrolled the shallows, their jointed limbs glinting with threat. Arthropods, armoured with calcified plates and spines, prowled tidal margins using speed and leverage to flip, grasp, and rip. Their segmentation allowed sudden bursts of motion. Their hardened exoskeletons made them living battering rams. In lagoons and reef edges, they exploited currents and ambush points shaped by coral shelters. Eurypterids, the sea scorpions, became monarchs of motion. Some genera, like Pterygotus, reached truly impressive sizes for their time, with flattened bodies and odonate-like swimming paddles that turned them into efficient pursuers. Their limbs could propel them with surprising speed. Their spiny anterior appendages grasped and held struggling prey. Fossil finds from the Bertie Formation and other Silurian Lagerstätten show articulated eurypterid carapaces alongside the remains of fish and other arthropods, evidence that these creatures occupied apex niches in multiple shallow environments. Their design was exquisite and merciless. Compound eyes, paddle limbs, crushing claws. Large, multifaceted eyes provided broad visual fields and sensitivity to motion. Paddles converted muscular power into thrust. Modified frontal appendages served as rakes, spears, or pincers. This combination of sensory acuity and mechanical force made eurypterids adept at ambush and pursuit. Fish responded in kind, evolving armor thick enough to turn aside their strikes. Early jawless and jawed fishes developed dermal plates, thickened skull roofs, and overlapping scale systems that deflected grasping claws. Ostracoderms and emerging placoderms protected vital organs in layers of bone or dentine, creating moving shields that changed how predators attacked. In turn, predators refined their jaws and cranial mechanics to generate greater bite forces, while prey evolved spines, burrowing behaviors, and tighter schooling to reduce individual risk. Each adaptation was a question answered by violence. Evolutionary innovation here reads like a sequence of gambits. One side presses a new offense, the other counters with defense, and selection adjudicates the outcome. Morphological shifts, heavier armor, quicker muscles, larger eyes carried energetic costs. Yet where resources favored risk, those costs paid off. The ecology of the Silurian seas thus became an arms race writ in bone and chitin, each escalation chiseling the blueprint of future life. In layered shale, fossils record the first chase scenes of natural history. Trackways, interrupted feeding scars, and tooth or claw marks preserved in limestone speak to dynamic interactions. A eurypterid clutching a fish, a placoderm crushing a shelled brachiopod, trilobites scattering under pursuit. Site by site, the Ludlow and Wenlock sequences, among them paleontologists, piece together these episodes, reconstructing food webs in which predators shaped prey evolution as surely as currents shaped sediments. The oceans are filled with hierarchy, predators, scavengers, survivors. Trophic complexity increased as niches multiplied. Primary producers fed grazers, grazers fed generalists, generalists fed specialists, and carrion fed a distinct guild of cleaners and detritivores. Chemical signatures in fossil organic matter indicate higher productivity and increasingly oxygen-rich waters in productive shallow basins, enabling active metabolisms and sustained predation. Ecosystems matured from simple food chains into networks with redundancy and resilience until the next perturbation. Climate stability gave this arms race time to refine its art. Where climate and sea level held steady for millions of years, selection favored specialization. Where conditions fluctuated, generalists gained an advantage. The Silurians' relative climatic steadiness in many shallow shelves permitted lineages to iterate on predatory designs, experimenting with speed, strength, sensory acuity, and social hunting. Over evolutionary timescales, successful strategies proliferated geographically, leaving regional faunas dominated by similar functional groups. Jawed fish emerged, turning passive feeding into pursuit. The evolution of jaws, a morphological rearrangement of gill arches and musculature, transformed feeding forever. Jaws allowed grasping, biting, and the mechanical processing of prey, enabling sustained predation rather than opportunistic filtering. Early gnathostomes, jawed vertebrates, paired this with paired fins for maneuver and control. Together, these features set the stage for increasingly active, directed hunting strategies across marine environments. From this invention came dominance, a lineage that would one day lead to us. The ecological consequences ripple far into deep time. Jawed fishes diversified into myriad forms, some becoming ambush predators in reefs, others chasing pelagic prey across open waters. Sensory systems refined lateral lines, electroreception precursors, and improved visual acuity, giving these hunters an edge. The evolutionary line from Silurian hunters to modern vertebrates is not a straight march, but the origins of directed predation and mobility are unmistakable here. The Silurian seas shimmered with potential, their balance teetering between abundance and collapse. For all their efficiency, these predator-dominated systems were fragile. Overfishing of key prey, shifts in sea chemistry, or climatic swings could topple hierarchies abruptly. Fossil horizons show both boom-crowded beds teeming with life and bust, sudden die-offs where the same predators vanish. The story is one of power wielded within ecological limits, always proximal to thresholds of collapse. Every struggle wrote a rule of survival that would echo across eras. Armor, speed, sensory specialization, and cooperative behaviors all emerged as solutions to the same fundamental problem: how to extract energy in a world of competitors. Those rules would be redeployed again and again across later epochs, forming the backbone of ecological strategy. Predators shaped the shape of life. Prey sculpted the limits of predation. And in those fading waters, power reached its height before time demanded change once more. The Silurian oceans, flush with predators and brimming with organized complexity, approached a peak of functional diversity. Yet Earth's story is cyclical. Moments of dominance invariably lead to vulnerability. The curtain would not fall today, but the forces of extinction, climate shift, and tectonic reworking were already at work, preparing a new chapter in which survival would mean different things. Echoes before the storm. In the hush that followed conquest, the seas exhaled a long, quiet breath. The great predators of the Silurian had found their rhythm, a balance between pursuit and prey, motion and stillness. Currents flowed steadily through reef labyrinths, scattering sunlight across coral domes and stromatoporoid spires. For the first time in eons, the planet's surface seemed to settle. It was as though Earth itself had paused to listen to the echo of its own pulse. For a moment, stability reigned. The continents, newly fused and smoothed by erosion, lay at peace under humid skies. Across shallow seas, carbonate platforms expanded into vast reef complexes, radiant fortresses built by coral and sponge. These reefs, teeming with trilobites, brachiopods, and early mollusks, stitched together ecosystems of astonishing intricacy. Each organism found its niche, every interaction part of a delicate equilibrium that stretched across the globe. Here, the water shimmered with clarity. Layers of plankton and algae turned sunlight into oxygen, while sediment settled softly to the seafloor. In cores of limestone that would one day harden into mountains, future scientists would read the story of this stillness, a brief geological interlude where carbon, calcium, and life itself aligned in fragile harmony. Stable carbon isotope ratios from these layers reveal an ocean in perfect chemical balance, its rhythms unbroken by catastrophe. Elsewhere, along coastal shelves, the first plants were learning to breathe land's thin air. Simple, spore-bearing pioneers, Cooksonia and its kin, clung to damp soil like green threads, weaving oxygen into the wind. Their roots began to pierce the upper layers of rock, crumbling minerals into fertile dust. Over time, these quiet invasions would change everything, drawing down carbon dioxide, cooling the atmosphere, and shaping the foundation for terrestrial ecosystems yet to come. Still, for all its calm, the planet was never truly motionless. Deep beneath the tranquil seas, magma pulsed in hidden arteries, pushing heat and pressure through the crust. Some volcanoes, long dormant, stirred faintly their gases, seeding clouds heavy with sulfur and ash. The signs were subtle, almost imperceptible: thin bands of iron in marine sediments, shifts in strontium isotopes, whispers of coming tectonic restlessness. The Earth, even at rest, rehearsed its next act. Through clear Silurian waters above the reefs, armoured fish drifted in slow patrols. The jawless ostracoderms shared space with early placoderms, creatures whose bony plates gleamed like forged metal beneath the sunlit shallows. Predation continued, but its violence had become ritual, a balanced exchange sustaining the order of things. In the fossil record, these ecosystems appear as layered tableaux, coral thickets entwined with shells, scales, and the faint impressions of fins. In these waters, time seemed elastic. Sediments accumulated grain by grain, each layer preserving a whisper of continuity. Whole reef provinces stretched across thousands of kilometers, from the margins of Laurentia to the edges of Gondwana. They formed a global belt of life, the planet's first great bioconstructed architecture. And yet, even these monuments of stability carried the seeds of future collapse. By locking away carbon in limestone, the reefs began to nudge the planet's atmosphere toward change. Somewhere unseen, the deep ocean began to darken. Circulation slowed, oxygen thinned, and pockets of anoxia spread in abyssal basins. To modern geologists, the redox signatures from this time depleted in oxygen isotopes, enriched in iron and sulfur, tell a quiet story of imbalance. Nutrient flows grew uneven, and the chemistry of the sea started to shift. The balance that life had so delicately woven was beginning to fray, thread by unseen thread. Even as equilibrium lingered above, subtle climate oscillations stirred the skies. Solar patterns and orbital variations modulated temperature, producing faint, wet-dry cycles across continents. Rivers carved gentle paths through coastal plains, depositing silts that bore the imprint of changing rain. Over time, these fluctuations grew bolder. The once steady carbonate deposition faltered, replaced by layers of shale rich in organic matter, the fingerprints of stagnation. Ocean circulation patterns were shifting, driven by tectonic changes and the deep restructuring of mantle convection. The calm surface hid a restless planet, its internal engines preparing to rewrite the map again. On quiet seafloors, life adapted as it always had. Benthic communities adjusted to dwindling oxygen, while new species evolved to thrive in low-energy environments. Sponges colonized dim slopes where sunlight could not reach, filtering what nutrients remained. Fossil traces from these zones, faint burrows, delicate fronds, record a resilience born of patience. Life, sensing the undercurrent of instability, did not resist it. It bent with it. Around their roots, the first terrestrial mosses began to spread across coastal mud. Their presence darkened the ground, trapping moisture and organic carbon. The land, long barren, was learning to retain life. Spores lifted into the wind, carried across new rivers and lakes. These invisible voyagers marked the beginning of terrestrial expansion, not yet forests, but the promise of them. Overhead, the sky shimmered with a new transparency, the atmosphere no longer veiled in volcanic haze, but washed clean by the long patience of photosynthesis. Oxygen levels climbed, molecule by molecule, until the air itself began to carry a deeper blue. High above, ozone thickened into a shield of invisible chemistry, scattering sunlight and softening the ancient glare. Beneath this evolving sky, ecosystems flourished in quiet confidence, unaware they were approaching a threshold. Every reef, every spore, every ripple of tide whispered the same inevitability. Evolution was gathering force, and somewhere in that stillness, the next transformation had already begun. Even in balance, life anticipates change. The biosphere, in its symmetry, becomes sensitive, each oscillation, each feedback magnified across scales. Coral growth modulated the carbon cycle, plant respiration tempered the air. The Earth functioned as a single living system, an orchestra of interlocking rhythms. And as always, when one section played too long in harmony, another prepared to shift the tone. Eventually, that shift would come. The seas that once nurtured coral cathedrals would turn unstable. The continents, newly green, would summon rain and erosion on an unprecedented scale. Vertebrates would venture onto land, following the rivers carved by ancient storms. But for now, the Silurian world stood in luminous stillness, a planet in equilibrium, poised on the brink of reinvention. Somewhere in the deep, the next chapter of creation stirred. Mantle plumes reorganized, ocean currents twisted anew, and spores drifted toward new horizons. The calm before the Devonian was not an ending, but a breath drawn between eras. The balance that life had achieved was both triumph and illusion, the fragile silence before the surge. And as the planet inhaled once more, the stage was set. From harmony to transformation, toward the dawn of the Devonian, when forests and vertebrates will reshape the planet once more. The Silurian was a world poised between silence and song, a planet rediscovering balance after chaos. Seas shimmered with new architects of life, while the first roots stitched land to sky. It was here that Earth learned patience, that creation is not sudden, but cyclical, sculpted by breath, by tide, by time itself. Every ripple, every leaf, every storm whispered the same truth, that life endures through rhythm. The echoes of that ancient calm still linger in every breeze we breathe today. Subscribe for more journeys into Earth's deep past.